You know that phrase? You've almost certainly read it in a dozen different pop science articles over the last few years. It usually goes something like, well, a quantum computer is incredibly fast because it tries every possible answer at the exact same time, and then it just reads out the right one.
Yeah, right.
Yeah.
It's like the single most pervasive myth in modern technology reporting. I mean, it sounds elegant, right?
Yeah.
And incredibly intuitive,
Oh, absolutely.
but also just fundamentally mechanically wrong.
Which is exactly why we are opening up a custom deep dive into this dossier today titled How a Quantum Computer Really Works. Because we're throwing out the superficial buzzwords,
Right.
right? We aren't just going to toss around terms like superposition or entanglement and expect you, the listener, to just accept them as magic.
Because it's not magic, it's physics.
Exactly. We are going to build a grounded mechanical understanding of the physics, the math, the actual hardware, and the algorithms that make quantum computing a reality. By the end of this deep dive, you're going to understand three absolute truths. First, amplitude is not the same thing as classical probability.
Right, huge distinction there.
Second, interference is the actual computing logic of a quantum machine. And third, error correction is the only realistic path to scaling these machines up, to actually solve world-changing problems.
Yeah, so to dismantle that first myth, right, the whole trying everything at once thing, we really have to look at the mathematical foundation of a quantum bit, or a qubit.
Okay, let's go into it.
So we write these states using bracket notation, like ket 0 and ket 1. That represents the two distinguishable base states. But the actual mathematical reality, like what's really happening, is that a qubit is a normalized vector and a two-dimensional complex Hilbert space.
Okay, wait. Let's translate two-dimensional complex Hilbert space into something a bit more tangible, because I feel like that is exactly where the distinction between probability and amplitude lives.
Yeah, that's exactly where it lives.
Because in a classical system, if I have a probabilistic bit, let's say, a memory cell that's been completely scrambled, and it has a 50% chance of being a 0 and a 50% chance of being a 1,
Right.
that bit doesn't have any hidden geometry. It is just a state of classical ignorance. Like, we just don't know what it is yet. It's already 0 or 1. We just haven't looked.
Exactly.
But a complex Hilbert space implies something entirely different for a quantum superposition, doesn't it?
It does. It means we are dealing with complex numbers. I mean, a classical probability is always a real positive number between 0 and 1. You can't have, like, a negative 20% chance of rain tomorrow.
Right, that would be absurd.
Exactly. But quantum amplitudes are complex numbers, meaning they have a real part and an imaginary part.
Okay.
And this gives them a magnitude, but crucially, it gives them a phase, a relative angle.
A phase.
Yeah. So when a qubit is in a superposition, it is not a 0 and a 1 at the same time, in the sense of, like, a hidden coin that has already landed and you just haven't uncovered it yet.
Which is the classic pop science metaphor.
Right, but that actually describes a classical mixed state. A quantum superposition is a pure state. It describes the mathematical structure of potential outcomes through their amplitudes and their phases.
So if a classical probabilistic bit is like a spinning coin, where it is definitely heads or tails at any given microsecond, it's just moving way too fast for our eyes to track. A qubit in superposition is a completely different physical entity.
Completely different.
It's more like a sound wave.
Yes, that's a much better way to think about it.
And just like sound waves in a room, these states have a phase that dictates how they interact with their environment, right?
And with
Each other.
Yeah, exactly. I mean, think about sound waves. You can have two waves that are perfectly out of sync. The peak of one meets the trough of another, and they just cancel each other out entirely.
Leaving total silence.
They're leaving silence.
Yeah.
But a spinning coin does not have a phase. You can't take two spinning coins, combine them, and somehow end up with 0 coins.
Right, that's impossible.
But you can absolutely combine two complex amplitudes in a Hilbert space, point them in opposite directions on the complex plane, and arrive at an amplitude of 0. And this capability, this interference, is the entire basis of quantum mechanics.
Wow. Okay, but at some point, we have to get an actual classical answer out of this complex wave system, right? Like, if I'm running a computation, I eventually need a hard number on a screen. I can't just look it away.
No, you can't. And that requires measurement. And measurement in quantum mechanics is, well, it's not passive reading.
What do you mean by that?
Well, in the classical world, you look at a book on a table and you just register its presence. Your act of looking did not physically alter the book.
Right, it's just sitting there.
But in the quantum realm, measurement is a physical, completely irreversible interaction.
Yeah, the dossier describes this using the Born rule. It calls it the bridge between the quantum wave and our classical reality.
The Born rule is central. It dictates that the probability of measuring a specific classical state is the squared magnitude of its complex amplitude.
Okay, the squared magnitude.
Yeah. But the really violent part is the aftermath of that. Upon measurement, the state collapses.
The wave is gone.
Entirely. The complex wave function, with all of its delicate, beautiful phase information, just vanishes.
Yeah.
The system is brutally forced into the classical state you just observed.
So if you measure a 0, it's just a 0.
Right. If you measure a 0, the qubit is now purely a classical 0. The phase is erased. Forever.
Which, I mean, that introduces a massive bottleneck. If looking at the system destroys the wave, how do we ever link multiple qubits together without ruining the math?
Right.
The dossier points to entanglement to solve this. Like, if I have two qubits, they can enter a state where they are completely non-separable.
Yes.
The classic example in the text is a state where the qubits are either both 0 or both 1, mathematically written as kit 0, 0 plus kit 1, 1, all over the square root of 2.
Right. That's a classic Bell state.
Yeah.
And the non-separability of that state provides correlations that completely defy classical physics. Well, Bell's theorem proved that we cannot explain this by claiming the particles had, like, hidden variables.
Like they secretly agreed beforehand.
Exactly. You can't say they secretly agreed to be a 0 or a 1 before they left the source. They are fundamentally linked as a single system. And this entanglement is the absolute core resource for everything useful in a quantum computer.
Everything.
Yeah, everything. It allows us to perform 2 qubit logic gates, which are necessary to build complex algorithms, and it's the foundation of quantum error correction.
Okay, but there is a massive sci-fi myth we need to address here regarding entanglement.
Oh, I know which one you're talking about.
Yeah, the idea that this instant correlation allows for faster-than-light communication.
Right, the Ansible from sci-fi.
Yeah.
Physics absolutely prohibits that through the no-signaling theorem.
Okay, break that down for me.
So, even though the measurement outcomes of 2 entangled particles are instantly correlated regardless of distance, like one could be here and one on Mars, the outcomes themselves remain random according to the Born rule. Yes, you cannot force your local entangled qubit to be a 1 so that a receiver on Mars instantly registers a 1. Because your result is random, the receiver's result is random.
So you can't encode a message in it.
Exactly.
Yeah.
You still have to pick up a phone, a classical speed-of-light limited channel, and call the receiver to tell them what you measured so they can decipher their own random data.
Okay, so no instant interstellar internet.
Nope. Sorry.
But let's look at the computational implications of this, because if measuring the system destroys the wave, strips away the phase information, and forces everything into a classical 1 or 0, I mean, measurement acts as a severe bottleneck.
It really does.
It's like this tiny keyhole through which all this massive quantum information must pass to enter our classical world.
It is the ultimate constraint. You cannot simply read out the entire superposition. It's impossible.
So to bypass that bottleneck, the computer has to do the heavy lifting before the measurement happens.
Yes.
Which brings us back to the myth. The true power of a quantum computer isn't parallel processing, it is controlled interference. And we engineer that interference using quantum gates.
Right.
But these aren't like classical logic gates, are they?
Not at all. Classical logic gates, like an A and D gate, are irreversible. If an A and D gate outputs a 0, you have absolutely no way of knowing if the inputs were 0 and 1, 1 and 0, or 0.
The information is just gone.
Gone. It's permanently lost to the environment as heat. But quantum gates are represented mathematically by unitary matrices.
Unitary matrices.
Right. And the defining property of a unitary matrix is that it is perfectly reversible and it preserves total probability.
Meaning the sum of all probabilities has to be 100%.
Always. The sum of all probabilities across the system must always equal 1. So every operation inside a quantum computer, right up until that final measurement, must be perfectly reversible.
The sources list the foundational gates that make up these unitary matrices. You have the poly-X gate, which basically acts as a bit flip, turning a 0 to a 1.
Yeah, that's the equivalent of a classical NOT gate.
Right. Then you have the poly-Z gate, which is a phase flip. The text says it leaves the magnitude alone but rotates the phase by 180 degrees.
Exactly.
The Hadamard gate, which puts a classical state into a superposition. and the CNOT gate, the controlled knot, which utilizes that entanglement we just discussed. So by layering these reversible gates, a programmer is basically choreographing a massive wave collision.
That's a great way to put it. The algorithm designer is mathematically aligning the phases across an exponentially large state space.
Okay, so how does that solve the problem?
Well, the objective is to engineer the circuit so that all the computational paths leading to the incorrect answers destructively interfere.
They cancel each other out.
Yes, driving their amplitudes to zero. And simultaneously, the paths leading to the correct answers constructively interfere, amplifying their presence. So when you finally execute the measurement at the very end, the Born rule heavily favors the correct answer.
Let's break down the mini example from the text, because I think it completely shatters the whole trying every answer at once myth.
Let's do it.
Okay, imagine a single qubit starting in the state 0. We apply a Hadamard gate. The qubit enters a 50-50 superposition. It acts as a wave representing both 0 and 1 with equal magnitude. If we measure it right then, we get a random coin flip, right? Half the time 0, half the time 1.
Right, that's standard superposition.
Yeah.
But here's the magic. If we delay the measurement and we apply a second Hadamard gate to that existing superposition,
Yeah.
we do not get random noise.
We don't get another coin flip.
No. The map dictates that we get exactly the state 0 again, 100% of the time.
Yeah.
The system returns exactly to where it started.
Wow. It's exactly like noise-canceling headphones, but applied to mathematics.
Oh, that's a perfect analogy, yeah.
Oh, yeah. Because noise-canceling headphones don't block the sound by building a thick wall. They measure the incoming ambient sound wave and actively play the exact inverse of that wave. The two waves meet, the phases destructively interfere, and the result is silence before the sound ever even hits your eardrum.
And that is exactly what the quantum algorithm is doing to the wrong answers before they hit the measurement bottleneck. The computational paths that could have led to the state, one, destructively interfered with each other during that second Hadamard gate.
It's active cancellation through phase manipulation.
Precisely. You aren't checking all the paths and keeping the best one. You are designing a physical, mathematical maze where the dead ends actively cancel out each other's existence.
That is mind-blowing. But, okay, if the engine relies on complex phase manipulation to cancel wrong answers, we have to look at the real-world problems that actually possess the right mathematical structure to exploit this trick.
Yeah, because not every problem does.
Right. Because adding qubits does create an exponentially large state space. Like, if you have n qubits, you have 2 to the power of n basis states.
True. But that exponential space does not automatically translate into an exponential speedup in computing power.
Because of the keyhole.
Exactly, the measurement keyhole. You can still only pull out one classical sample per run. So to achieve a true speedup, the problem's underlying structure must allow for that massive choreography of interference we just talked about.
And the seminal example of this, the one that made everyone panic, is Peter Shor's algorithm.
Oh, yeah. Shor's algorithm changed everything.
It discovered how to factor large numbers exponentially faster than any known classical algorithm.
Which, triggered a massive crisis in modern cryptography.
Right, because entire security protocols, like RSA encryption, rely entirely on the fact that factoring a massive number back into its original prime components takes classical computers millions of years.
Exactly. It's easy to multiply two primes together, but almost impossible to reverse it classically. But Shor recognized that factoring is secretly a problem of finding hidden periodicity.
Hidden periodicity.
Yeah, it's about finding a repeating pattern in an astronomically large sequence of numbers.
Okay.
So he utilized a mathematical operation called the quantum Fourier transform paired with phase estimation.
And what does that do?
The quantum Fourier transform is just remarkably efficient at finding periods hidden within a massive superposition. When applied, the correct period constructively interferes, while all the incorrect, non-repeating frequencies destructively interfere and just fade to zero.
Wow.
Yeah. It proved that a sufficiently large quantum computer could literally shatter the mathematical bedrock of internet security.
That's terrifying, honestly.
It is.
But the dossier also highlights another famous one, Love-Grover's algorithm, which is designed for unstructured search, like finding a specific needle in a completely unsorted digital haystack.
Right. Grover's algorithm employs a technique known as amplitude amplification.
Okay, how does that differ from Shor's?
Well, it applies an oracle, which is basically a function that recognizes the correct answer to repeatedly apply a phase flip specifically to the marked solution. And then it reflects the average amplitude of all the states.
It reflects the average.
Yeah, so step by step, iteration by iteration, it pushes the amplitude toward the correct solution. amplifying its probability before you ever make a measurement.
But the speedup for unstructured search isn't exponential like Shor's, is it? The text classifies it as a quadratic speedup.
Right, a quadratic speedup.
So it reduces a search of n items to the square root of n.
Exactly. And to contextualize what that means practically, the sources outline this complexity class called BQP.
Bounded error quantum polynomial time.
That's the one. This class represents the set of all problems a quantum computer can solve efficiently.
And bounded error just means?
It simply means we accept a small probability of measuring the wrong answer because, we can easily run the fast circuit a few times to verify the result.
Right, that makes sense.
Right.
But the critical limitation here, and this is something that gets glossed over in the news all the time, is that complexity theorists do not believe BQP contains NP-complete problems.
No, they don't. And that's a huge deal. The general public assumes quantum computers will just instantly solve things like the traveling salesman problem.
Where you need to find the absolute shortest route connecting a massive number of cities.
Exactly. Or like complex global supply chain scheduling or intricate protein folding optimizations. People assume the machine will just try all routes at once and spit out the best one.
Because of the myth?
Because of the myth. But quantum speedups demand highly specific mathematical structures, like the Fourier structure in Shor's algorithm. Without that structure, you cannot choreograph the interference.
So for everyday applications like running a web server or managing a relational database or brute forcing a chaotic optimization problem without structure, classical logic remains vastly superior.
Oh, vastly. It's not even close.
Let's look at the reality of Grover's quadratic speedup then. Because if I have an unsorted database of 1 million items, a classical computer needs roughly 1 million steps to check them all.
Right.
But Grover's algorithm only needs the square root of 1 million, which is 1,000 steps. That is a massive theoretical advantage.
Theoretical, yes.
But in the physical laboratory, the friction of actually operating the quantum hardware is enormous. I mean, setting up dilution refrigerators, firing calibrated microwaves, dealing with constant errors. Couldn't that quadratic advantage entirely vanish against the sheer clock speed of a classical silicon chip that's executing billions of operations per second?
Oh, absolutely. The physical overhead absolutely devours quadratic speedups in the near term.
Wow.
The time it takes to execute a single high-fidelity quantum gate is significantly longer than a classical clock cycle.
So classical is just too fast.
Yeah. An exponential speedup, like Shor's, pulls away so violently as the numbers get larger that it overcomes the hardware friction.
It just outpaces it.
Right. But a quadratic speedup is constantly fighting a losing battle against the sheer speed and reliability of modern silicon.
Which brings us to the actual hardware, the friction in the laboratory, because there is no single quantum computer right now, is there?
No, not at all.
Like, the industry is not standardized on silicon CMOS transistors the way classical computing is. There are multiple competing physical platforms, and each one is making these distinct, frankly painful trade-offs between coherence times, gate quality, connectivity, and the ability to actually scale up.
It's a wild west of physics right now. But the leading candidate currently is superconducting qubits.
Okay, let's start there.
These are microfabricated circuits acting as artificial atoms. And the most common design is called the transmon.
The sources mention that transmons are built using Josephson junctions. What exactly is that?
Okay, so a standard classical electrical oscillator has evenly spaced energy levels, and you hit it with a microwave pulse to push it from the 0 state to the 1 state. That same frequency might accidentally push it from 1 to 2.
Which completely ruins your binary 0-1 qubit.
Exactly. So a Josephson junction, which is essentially a microscopic layer of non-conducting oxide sandwiched between two superconductors, adds a crucial nonlinearity to the circuit.
Nonlinearity.
Yeah. It squishes the energy levels together at the higher ends. This means the specific microwave frequency required to jump from 0 to 1 is uniquely tuned.
Ah, so you can isolate it.
Exactly. It allows us to isolate those two states and use them as a pristine qubit.
But the operational requirement for these things is brutal. I mean, they require massive dilution refrigerators to operate at fractions of a degree above absolute zero.
They do. The energy difference between the 0 state and the 1 state in a transmon is incredibly small. If the chip were at room temperature, the ambient thermal energy, the literal vibration of the atoms in the surrounding metal, would constantly bombard the qubit, randomly flipping it and destroying the computation instantly.
So it's literally too loud for the qubit to think.
Yes. Freezing the system suppresses that thermal noise.
Okay, so that's superconducting. Then there are ion traps. And instead of building artificial atoms, they use real atoms.
Real actual atoms.
You suspend an ion in a vacuum using electromagnetic fields, and you control it with lasers.
It's honestly some of the most elegant physics we have. The qubit is defined by the natural energy levels of the ion's electrons.
Okay.
And to perform multi-qubit gates, to entangle them, you use lasers to physically push the ions so they vibrate together in the electromagnetic trap.
The sources refer to this as a phonon bus.
Right. They communicate their quantum information through shared vibrational modes, phonons.
That's wild.
And the advantage is massive coherence times. The states last a very long time because the ions are perfectly isolated in a vacuum.
But there's a downside.
Always. The downside is scalability. Wiring millions of microscopic lasers to precisely target millions of levitating atoms at a massive grid is an optical nightmare.
I can imagine. We also have neutral atoms, which use optical tweezers, which are basically highly focused laser beams to hold the atoms in place.
Yeah, neutral atoms use Rydberg excitations.
What's a Rydberg excitation?
So, by hitting an atom with a laser, you excite its outer electron into a massive orbit, turning it into a Rydberg atom. In this state, it strongly interacts with its neighbors over relatively long distances, which allows for entanglement.
Okay.
And this platform is proving incredibly useful for quantum simulations. Physicists can arrange the atoms in specific 3D grids to simulate complex, undiscovered materials.
And finally, photons.
Yeah.
Particles of light. The dossier notes they are perfect for transporting quantum information because they barely interact with their environment at all.
Oh, they're fantastic for transport. You can send a photon through miles of fiber optic cable at room temperature, and it perfectly maintains its quantum state.
But
the problem is that photons also refuse to interact with each other.
Oh.
Yeah. If you need two photons to cross paths and form a deterministic logic gate, they will simply pass right through one another.
Like ghosts.
Exactly like ghosts. Building reliable two-photon logic gates remains a massive, massive technological hurdle.
So all of these platforms, regardless of the approach, are currently trapped in what the industry calls the NISQ era. NISQ, Noisy Intermediate Scale Quantum.
Yeah, the NISQ era. Noise is the great enemy of the quantum state.
In the formal mathematical models, noise is treated as a quantum channel, specifically a CPTP map, which stands for a completely positive trace-preserving map.
Right, that's the formal math. But practically, it manifests in two fatal ways.
Okay, what are they?
First is relaxation, known as T1 time. This is where the qubit simply loses its energy to the environment and decays from a 1 back down to a 0.
It just runs out of gas?
Exactly. And second is decoherence, known as T2 time. This is the loss of the relative phase.
The phase, the thing we need for interference.
Yep. Without the phase, you have no interference.
Hmm.
Without interference, you have no computer.
To put this in perspective, as of early 2026, the dossier mentions IBM's Quantum Heron chip is sitting at 156 qubits, and Google's Willow chip is at 105 qubits. I mean, a modern smartphone has billions of transistors, so 100 qubits sounds almost insignificant.
I know, it does sound small, but the sources make a really critical point here. Physical qubit count is just a vanity metric in the NISQ era.
A vanity metric.
Completely. Having 10,000 noisy qubits is utterly useless if they decohere before you can finish a single algorithm.
Right.
The metric that actually dictates computing power is fidelity. Fidelity is the mathematical measure of how closely the messy, real-world physical operation in the laboratory matches the perfect, idealized unitary matrix on your whiteboard.
So we are essentially trying to build a massive house of cards during an ongoing earthquake.
Yes.
Because the moment the environment interacts with the system, a stray thermal photon, a tiny fluctuation in the magnetic field, even a microscopic vibration, the decoherence sets in, the wave collapses, and our carefully engineered interference pattern just falls apart.
Everything just crashes down.
So how do we ever plan to run Shor's algorithm, which requires millions of perfect, coherent operations? Like if the earthquake never stops, how do we build the house of cards?
We use the ultimate quantum hack, error correction.
Now, in a classical computer, error correction is pretty straightforward, right? If a hard drive wants to protect a file from a random bit flip, it just makes 3 copies of the file.
Right, simple redundancy.
If 1 bit flips due to a cosmic ray or whatever, the computer reads all 3 copies, sees that 2 are identical and 1 is different, takes the majority vote, and fixes the error. Why can't we just copy the qubits?
Because doing so violates a profound law of quantum mechanics known as the no-cloning theorem.
The no-cloning theorem.
Yeah. It is mathematically impossible to perfectly copy an unknown quantum state. If you try to write a mathematical operation that takes an unknown state A and a blank state B and outputs two perfect copies of A, you violate the fundamental linearity of quantum mechanics.
The math completely breaks down.
It completely breaks. Furthermore, physically, to copy a state, you would have to measure it to know what to copy.
Oh, and as we established with the Born rule.
The moment you measure the superposition, you collapse it. You destroy the very data you were trying to preserve.
Man, that is a brutal catch-22. If we cannot copy data to protect it, and the data is constantly decaying due to hardware noise, error correction seems fundamentally impossible.
It seems that way, yeah. But the solution lies in stabilizer codes. Since we cannot copy a single quantum state, we take the fragile quantum information and distribute it across many physical qubits through complex webs of entanglement.
Okay, so we smear the information out over a larger physical area.
Exactly. And to maintain that information, we perform what are called syndrome measurements.
Syndrome measurements.
Right. We have to identify if a physical error occurred, like a poly X bit flip or a poly Z phase flip, without ever directly measuring the logical data itself.
Okay, wait. How do you check for an error in the data without looking at the data? That doesn't make any sense.
It's brilliant, actually.
Yeah.
You measure the relationships between the qubits, not the qubits themselves.
Okay, give me an analogy.
Imagine you have two closed envelopes, each containing a number, and you need to know if one of the numbers accidentally changed. But you are strictly forbidden from looking at the numbers themselves.
Okay.
You introduce a third envelope, a helper qubit. You perform an operation that checks the parity of the two data envelopes, whether their sum is even or odd, and you write that parity result into the helper envelope.
Oh, I see.
You then open that helper envelope. If it tells you the sum changed from even to odd, you immediately know an error occurred in one of your data envelopes.
But you still have absolutely no idea what the original numbers were.
Exactly. You protected the data by never looking at it. You are measuring the error signatures, the syndromes, rather than the state itself.
That is incredibly clever.
Isn't it?
Yeah.
We constantly measure these syndromes across the system. And the leading paradigm for scaling this up is called the surface code.
The dossier explains that the surface code places physical qubits on a 2D checkerboard grid.
Right. So half the qubits on the checkerboard hold the actual data. The other half are the measure qubits, the helpers. And they are constantly interacting with their neighbors, checking parities, and reading out a massive continuous stream of classical data.
Just spitting out helper envelope results.
Exactly. And a classical supercomputer sits adjacent to the quantum chip inside the laboratory. It runs incredibly complex decoding algorithms like minimum weight perfect matching to trace those error signatures back to their exact physical origin.
So the classical computer is playing detective.
Yes. It calculates where the bit flip happened and applies a corrective microwave pulse in real time, completely fixing the error without ever collapsing the overarching logical wave function.
Which introduces the most vital distinction in quantum hardware. Physical qubits versus logical qubits.
Yes, this is so important.
A physical qubit is the actual noisy piece of hardware inside the dilution fridge, right? Like the individual transmon.
Right.
But a logical qubit is the single, pristine, mathematically perfect piece of quantum information that is encoded across a massive grid of those noisy physical qubits using the surface code.
Exactly. And the math behind fault tolerance reviews a stark reality. If the physical error rate of the hardware drops below a specific mathematical threshold, the surface code actually corrects errors faster than the noise can accumulate them.
Meaning you win the race.
You win the race.
Right.
Once you cross that fault tolerance threshold, you can theoretically compute indefinitely.
But the overhead is staggering. If I want to run Shor's algorithm, I might need, what, a few thousand perfect logical qubits?
Roughly, yeah.
But if each logical qubit requires hundreds or thousands of physical qubits just to constantly run the parity checks of the error correction grid, I mean, building a machine that can break RSA encryption might require hundreds of thousands, if not millions, of physical qubits.
Millions, yes.
Yeah.
We are celebrating chips with 150 physical qubits today,
Yeah.
and we realistically need millions to unlock the true potential of the technology. It is the defining hardware engineering challenge of the century.
So with all this complexity, complex amplitudes, wave interference, dilution fridges, and massive 2D error correction grids constantly spitting out parity checks, how does a human being actually sit down and program this machine? Like, what does the code even look like?
Well, the standard model we have been discussing, layering unitary gates in a sequence, is called the circuit or gate model. But the dossier actually outlines two other major computing paradigms.
Okay.
The first is measurement-based quantum computing, or MBQC.
MBQC. And the text says this entirely flips the script. Instead of applying gates to a blank slate of qubits, you start by creating a massive, highly entangled block of qubits called a cluster state.
Right. The cluster state acts as a universal resource. The actual algorithm consists entirely of performing a very specific adaptive sequence of single qubit measurements.
So you're just measuring them one by one.
Yeah. By selectively measuring and destroying the cluster state piece by piece, you mathematically sculpt the logic into existence. The measurement itself performs the computation.
That's fascinating. You're chipping away at the marble block.
Exactly. You're carving the algorithm out of the entanglement.
The other paradigm the text mentions is quantum annealing. And there is a massive misconception in the public sphere regarding annealers, because you often see companies boasting about machines with thousands of qubits today.
Oh, yeah. This frustrates physicists to no end. In almost all cases, those high QUID-MED count machines are quantum annealers. They do not use the gate model.
Okay, so how do they work?
They operate on a principle called adiabatic evolution. You physically encode your optimization problem into the energy landscape of the superconducting chip itself.
Like physically building a terrain?
Yes. You then slowly let the system cool down. The laws of thermodynamics dictate that the system will naturally settle into its lowest possible energy state, which ideally represents the optimal answer to your problem.
But the critical limitation here is that quantum annealers are not universal quantum computers.
They are not. They cannot run Shor's algorithm. They cannot run the surface code for fault-tolerant error correction.
So they are limited.
Very. They are highly specialized, noisy machines designed almost exclusively for finding decent heuristic solutions to complex scheduling or routing problems, but they completely lack the rigorous mathematical guarantees of the universal gate model.
Good to know. So returning to the universal gate model, the software frameworks managing these machines are entirely different from classical coding environments, right? The dossier contrasts IBM's Qiskit and Google's Cirq.
Yeah, these are the two heavyweights right now. Qiskit is a comprehensive framework for managing the entire quantum pipeline. You define the abstract problem, compile it into a sequence of idealized logical circuits, and then perform transpilation. Transpilation is where the compiler maps your perfect, idealized gates onto the messy, constrained reality of the specific hardware chip.
Okay.
It physically routes the information to account for which physical qubits are actually connected to each other on the 2D grid.
Right, because not all qubits talk to every other qubit.
Exactly. Now, Cirq approaches the problem from the bottom up. It is built heavily around the immediate realities of the NISQ era, forcing the programmer to think explicitly about hardware connectivity, native gates, and physical layout from the very first line of code.
It's less abstract, more hands-on.
Very hands-on.
But the workflow itself is fundamentally statistical. When I write a classical Python script, I run the code and it hands me a definite number, like 2 + 2 is 4.
Right.
But because of the Born rule, the inherent randomness of measurement and the noise in the hardware, a single run of a quantum circuit, which the industry calls a shot, only gives you one random classical sample.
Right. Programming a quantum computer is really about setting up a highly complex probability distribution. You define the experiment, optimize the gates for the hardware, and then you execute thousands of identical shots.
You run the exact same program 10,000 times in a row.
Yes.
And what comes back is not an answer, it is a histogram.
A distribution of counts across the thousands of runs.
You then employ classical statistical post-processing. You apply error mitigation techniques and calculate estimators to infer what the true mathematical signal is, hidden inside that noisy distribution.
You aren't really writing software in the traditional sense. You are acting as an experimental physicist.
Yeah.
You are setting up an incredibly delicate physical experiment, establishing a probability distribution, running it 10,000 times, and doing rigorous statistical inference on the static to find the signal. It is physics manifested as code.
Physics manifested as code. That is incredible.
Okay.
We have covered an immense amount of ground today. From the foundational math of complex vectors to the engineering nightmare of fault-tolerant parity checks. Let's synthesize the 3 ultimate truths we promised at the beginning.
Let's do it.
Number 1, amplitude is fundamentally different from classical probability. It is not a state of ignorance about a hidden coin. It is a complex wave with a magnitude and a phase. Number 2, the true power of quantum computing isn't parallel processing. It is the intricate choreography of interference manipulating those complex phases through reversible unitary gates. So the wrong answers destructively cancel each other out, and the right answer amplifies before hitting the measurement bottleneck.
That's the engine.
And number 3, true scaling relies entirely on logical qubits. To solve world-changing problems, we have to build massive 2D grids of physical qubits running continuous parity checks just to protect a single piece of delicate quantum information from the noisy earthquake of reality.
Those are the absolute mechanical realities of the technology. But, if we pull back from the engineering for a second and look at what the math is actually telling us about the universe, I want to leave the listener with a final thought to ponder.
Okay, let's hear it.
We have spent this whole deep dive treating quantum mechanics as a fragile, delicate thing, a wave that collapses the moment our big, solid, classical world interacts with it. But the physics actually dictates that the most fundamental layer of our universe calculates reality using complex amplitudes, reversible unitary matrices, and wave interference.
Right.
The quantum world is the underlying engine of existence. So what does that say about our everyday experience? Is the solid classical world we see around us, the hard ones and zeros, the definite objects, the irreversible flow of time and thermodynamics, is that actually the real world? Or is everything we experience merely the exhausted, collapsed remainder of a much richer, invisible quantum computation that is constantly running everywhere, just beneath the surface of reality?
Are we just the readout?
Exactly.
The collapsed static after the universe runs its algorithms. We started this deep dive talking about a spinning coin, but it turns out the coin isn't real at all. It's just the sound of the wave crashing.
Yep.
Thank you for joining us on this deep dive. We'll leave you with that to process.